Hello, my name is Medea Rosenskaite, and this is Lab 4, covering oscillations for Physics 2211 at Georgia Tech. The purpose of this lab was to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. We used Tracker to analyze the footage, and we used GlowScript to predict changes in energy. The goal of the lab was to determine if the model satisfied the energy principle, and we found out that it does, and the predicted model was very closely similar to the observed. The physics principles that we applied in this lab were Newton's second law and the energy principle. Newton's second law says that momentum over change in time gives us the net force, which is also equal to the sum of all the forces acting on a system, which here is spring and gravity. The energy principle states that the total change in energy in the system is equal to the work done by the surroundings on the system, as well as the transfer of thermal energy on the system, denoted by Q. We are focusing on the spring force and the gravity once again. The setup of this experiment was a spring attached to a fixed point which had a mass attached to it, and we knew that the mass was 0.402 kilograms. We knew that the relaxed length of the spring was 0.7 meters. We also knew that it started from rest, so the initial velocity 0, 0, 0, and then we found the initial position from the tracker analysis. To calculate the spring constant and the relaxed length of the spring, we used the period of oscillation, which is equal to 2 pi times the square root of m over k. We rearranged that to find k, and to find t, we used the graph from the tracker analysis and just made 3 periods, and we divided it by 3 to find the average. And then we just put that in the equation because we know f net equals 0. Here is the code that I used in GlowScript. Highlighted, you can see all of the things that I've changed. The mass of the ball, which was given to us, the initial position, initial velocity, gravity, spring constant, and L naught, which we found. And then we had to define the length of the spring and the system energies, which we did using the equations. And then in the while loop, we calculated the forces using known equations as well. The GlowScript code modeled the oscillation of a mass on a spring going side to side using the components from our real-life experiment that we found the total energy of using the program tracker. This picture over on the left came from the code and models the path of the mass oscillating on the spring. As you can see by these two lovely graphs down here, the x and y components of the data from tracker and the code line up fairly beautifully. This means that our apparatus did what it was supposed to do, and the experimental data matched the predicted values calculated from the code. In this top graph, there are a lot of colorful curves, so let me break it down for you. The orange line is the change in total energy, so it stayed fairly consistent, oscillating around 0 joules. Our main curves in this graph are the red and green lines, which correspond to change in spring potential energy and change in gravitational potential energy. These two energies are equal and opposite. This basically means that when the spring was stretched the most at the bottom of its path, the gravitational potential energy was the smallest. As the spring went up, the gravitational potential energy increased and the spring potential energy decreased because the spring was the least stretched out, so it wasn't trying to get back to equilibrium. We can see that when they intersect, as one increases and the other decreases, that the total energy is the average of where those two curves intersect in the blue line, which represents the change in kinetic energy. The change in kinetic energy always stays pretty consistent because since the spring is oscillating, it is repeating its motion, so it has speed and then it stops and then goes the opposite direction. So the kinetic energy just goes back and forth. Another thing to note is that you can probably notice that the curves differ more in the y direction than in the x direction, so I'm going to talk about that in the next slide. A possible reason that the y direction graph is slightly different than the predicted versus the observed was because we didn't account for other forces like drag or friction, and the code models the experiment in a closed ideal simulation. Another possible source of error was that I didn't click exactly on the center of mass in the tracker analysis. After conducting this experiment and compiling all of our data, we have to conclude whether the energy principle is satisfied, and it is in fact satisfied because the energy principle states that the change in energy must be equal to the work done by the surroundings. And in the change in energy versus time graph, we see that change in energy remains constant and around 0 because the sum of all the energies is equal to 0. Also, we can conclude that there's nothing acting on the closed model system because we made our system, the spring and the earth, that way we don't have to use work done by gravity, and we use gravitational potential energy. And a comparison of the oscillation periods, they're the same because we use the same time interval, as you can see in these two graphs. Thank you.